Hello, hello. Got my trusty cup of joe. We're gonna do some math, and I don't have a rhyme for that part. So we're gonna do part 2 of my, what the heck? Integrals of powers of the tangent function video that I did a while ago and then kind of got sidetracked by some laws of trig stuff. Because of a previous comment on that video or on the post I made on Reddit that sort of showed a much simpler way of attacking this problem, I'm going to finish what I'm doing now, and then at the end of the last video I'm going to show this much easier way of considering this problem using the beta function. Very strange. But Papa Flammy has covered a lot of those before already, so I won't be trying to demonstrate any facts about that function, like how you can represent it in the way that I'm going to. Just watch his video on it. Today I'm just going to continue sort of the how you might discover this on your own kind of path. So I'm going to continue from where we left off in the last video, and we'll see how far we get. So if you remember in the last video, we were investigating the values of integrals that look like this. So we defined I of little k, capital I of little k, to be the integral from 0 to infinity of the natural logarithm of t to the power of k, that's the function input for the independent variable k, all over 1 plus t squared with respect to t. So we're integrating over this function, and we're seeing what it gives us in the area under the whole curve at different non-negative powers. So k is 0, 1, 2, 3, so non-negative integer powers. And we were able to deduce that if we let k be an even number and we input that into the function, we find that this ends up being equal to just 2 times the integral from 0 to 1 of that same integrand, which is to say that the area under the function from 0 to 1 is equal to the area under the function from 1 to infinity. So this is also equal to 2 times the integral from 1 to infinity of the same integrand, but because this is a finite interval, it just seems easier to handle, perhaps. And we were also able to show that when k is odd, that this integral evaluates to 0, because though the area under the curve from 0 to 1 is the same as the area under the curve from 1 to infinity, one of those is beneath the x-axis whereas the other is above it, so they are exactly negatives of each other and they cancel out, and you just get 0. And that's actually going to be interesting later on in the video. This is going to come up as it's going to cancel a bunch of stuff, and it's going to be really nice. And we were able to show without much trouble that I at k equals 0 is pi over 2. Simply because when you plug in 0, you get 1 in the numerator, and the antiderivative of 1 over the quantity 1 plus t squared is the inverse tangent, the arctangent function. This function at infinity is just pi over 2, and it's 0 at 0, so it just evaluates to pi over 2. And so what we're going to do today is we're going to come up with a recursive way to evaluate this function, right? What is like the different values of I of k at values other than just 1. But because we have it at 0, we can use this as a base case, and then the recursive definition is going to work. So what we need to do is actually try to evaluate this integral using complex analysis. So if you're not familiar with what complex analysis is, it's simply just calculus that involves complex numbers, and that requires you to prove some new things about calculus that you didn't know prior, like extra restrictions, but it also opens up a world of much more interesting topics, and I find it to be much more rewarding than for example, real analysis, though both are very interesting subjects. But with one slight omission of the proof on the way to the conclusion, I can show that this is equal to a really interesting sequence of numbers, right, for different values of k. So if you'll follow me down this path, I think it'll be pretty interesting. So we have to do what's called a contour integral to try and evaluate what this is, because it's an improper integral because one of the bounds is unbounded. So we need to employ the sort of special tactic of contour integrals, which is otherwise mundane in the context of complex analysis. It's just I've never done one on the channel before. And so I'm going to do that now. So essentially what we have to do is we have to consider the integrand. So at the moment we're just having a look at the function that was under the integral sign. And we're now not considering k to be our independent variable, but z is now. So the variable that we were once taking the integral with respect to, because if you recall there were t's there and we were doing dt under the integral, that is now the independent variable. So we're taking a look at this function with a complex variable. So in complex analysis, z is just a complex variable, right? It's x plus I times y, where x and y are real numbers and I is the square root of -1. It's just a complex number, right? And so we're going to be doing an integral within the complex plane. So I need to draw a complex plane, which is of course just the two-dimensional plane where the horizontal axis is considered to be the real numbers, the real number line that we're all used to. So you usually notate that capital R-E, and the vertical axis is the imaginary axis, capital I-M. And we're going to highlight a few things on this imaginary axis, which is the points where this function is undefined. And it's undefined in a few ways. So in the subject of real numbers, a function can be undefined because you're taking the even root of a negative number, like the square root of -x, right? And whenever x is, if it's a negative number under the radical, then it's an imaginary or complex number and it's not on the real number line. That's no longer a problem with complex numbers because we have a completely closed set, I guess you would say, with the complex numbers, because any operation that you can do, essentially, keeps you within the set of complex numbers. So even roots of negative numbers are perfectly fine, but dividing by 0 is really the only problem. That's when it's an issue. And so when the denominator here is 0, and actually when you take the natural logarithm of 0, that is also undefined. It goes to -infinity if you approach it from the right. On the real number line, right? It goes down like that, down to -infinity as you get closer to 0. So the points where this function is undefined are when the denominator equals 0 and when z is 0, because you're taking the natural logarithm of 0. So we need to rewrite this function. And we're going to rewrite it with the denominator factored. So this is equal to the natural logarithm of z to the power of k. And how do we factor this? Well, we can do the difference of squares, we just need to be clever. So I'm going to rewrite it as, this is equal to z squared plus 1, right? So I can rewrite this as z squared minus I squared. And that's because I squared is -1 by definition, right? I said it was the square root of -1. So then we'd have z squared minus -1. And z squared minus -1 is equal to z squared plus 1, which is that. So these two things are equal. But because this is now a difference of squares and is perfectly well defined in the complex numbers, this is equal to the natural logarithm of z to the power of k over z minus I times z plus I. Right? And that's actually how you factor a sum of squares. You have to go into the complex numbers, and that's how you do that. So now we can clearly see that the denominator is going to be equal to 0 when z is equal to I, and when z is equal to -I. So we have to notate that on our complex plane. So I'm going to do this and put a little circle, a little empty circle, where -I is on the imaginary axis, because that will represent a pole of the function, where the function diverges because you're dividing by 0. And also at positive I, right, that's also a problem. And also at 0, because the natural logarithm of 0 is undefined. So those three poles are the problem, and you just notate them with 3 little open circles. And now I'm going to show you what curve we're going to integrate over. We're actually going to ignore the pole at -I. I just wanted to be consistent and show that it is there, we just don't actually need it to solve this problem. So we need to be really clever. So we need to do an integral over a closed contour, a closed loop, that goes around in a way that works best. So I'm just going to draw it first, and then I'm going to explain why this works. So it looks like this. That's supposed to be a semicircle. So this is like a half donut shape. Okay? And what it is it's got this horizontal bit on the real axis from little r to big R. So little r and big R are real numbers, right? And so we have a similar horizontal one from negative big R to negative little r. So it's like the mirror image. Because what it is, this is a semicircle with radius big R, and this is another semicircle with radius little r. And so and the arrows notate the direction we're going around the curve. So this is taken in the positive sense, which means we're going counterclockwise around the curve, and you can just follow the arrows. There's one on each section. And we're going to take an integral around this entire closed curve, specifically around the pole I, and specifically avoiding the pole 0. We actually don't even have to consider the pole at -I. By the way, we've labeled the little semicircle little lambda and the big semicircle big lambda. Okay? So we've got 4 sections. This bit, the horizontal bit, the big semicircle, the other horizontal bit, and the little semicircle. And what's essentially going to happen is we're going to let little r go to 0. So it's going to sort of go around the pole at 0, but never touching it. But we're going to take the limit and see what happens as we take the integral over that curve. And we're going to let big R go to infinity. Because what that will do is it will give us this horizontal integral from 0 to infinity in the limit. And that's sort of what we're looking for, right? We're looking for this integral from 0 to infinity of this integrand, right? That's the whole point. That's what we're trying to evaluate. And essentially, what we know is that we can actually calculate what the whole curve, the integral over the whole curve, has to be equal to. And it's using something called Cauchy's residue theorem. And essentially what it says is you can evaluate a closed contour integral based on the poles of the function that occur inside that contour. And how you would write it is this integral over the entire contour, we're calling it capital C, this whole contour is capital C, of this function, right, we're taking it over this function, right, this is what we're trying to evaluate, over f of z, with respect to z, is equal to 2 times pi times I times the residue of the function f of z at the pole, the sum of the poles inside the curve. In this case, there's only the pole at positive I, so at z equals I. And what this is it's essentially what do you get when you plug in I into the function when you eliminate the problem point? So z minus I in the denominator is what's going to equal 0 when you plug I in for z, right? So if you eliminate that, if you just got rid of that, so if you multiplied this function by the factor z minus I and canceled it out, what would you get if you then plugged I into what's left? Well, you would get the natural logarithm of I, whatever that is, to the power of k, divided by z plus I. But this is made 0 by negative I. I'm sorry, yeah, it's made 0 by negative I, so plugging I into it isn't going to give us 0. So if I, essentially what the residue of f of z at z equals I is when you plug in I to just this function. And so all we have to do is plug I into this well-defined function at I, and we'll get what it has to be equal to. And this is 2 pi I times just plugging in I to what's left. So we get the natural logarithm of I to the power of k, should probably move it up there, to the power of k, over I plus I, right? Because it was just z plus I in the denominator, so we're just plugging in I there. And we have to ask ourselves, what's the natural logarithm of I? Well, the natural logarithm of I, we have to do that from Euler's formula, right? And so I'll prove that at some point. So we know that from Euler's formula that we have e to the I pi is equal to negative 1. And so if we take the square root of both sides, which is the same as the 1/2 power, we get that e to the I pi over 2 is equal to, what's the square root of negative 1? That's I. And now we have to take the natural logarithm of both sides. We get the natural logarithm of I is equal to, well, those are going to cancel, we just get the power, and we get that it's equal to I pi over 2. Because this is in the principal branch, right? It's pi over 2 because we're in the angles between 0 and pi. So pi over 2 is in the middle of that, it's in the principal branch, so this is perfectly well defined, and it's just I pi over 2. So the natural logarithm of I is I pi over 2. So we get 2 pi I times I pi over 2 to the power of k divided by 2I, right? That's what we end up with. The 2 i's cancel, right? Because it was 2 pi I over 2I, and the 2 times i's cancels. And we're left with a simpler expression, and we get pi times the quantity I pi over 2 to the power of k. So this is what the integral over this function is equal to when you do it around the whole curve. Okay? So that's what we're going to have this set equal to. So I'm going to erase this drawing now. I'm going to write this whole contour integral in terms of the integral over the 4 pieces, right? The 2 straight parts and the 2 semicircle parts. Okay? So, and I'm going to set it equal to that because that's what we're going to end up with. So I'm going to erase all this now. So this is how I've written it. We have the integral over the first horizontal part from little r to big R. We have the integral over the larger semicircle that we called capital lambda. We have an integral over the second horizontal part from negative big R to negative little r. And we have the integral over the smaller semicircle that we called little lambda. And we understand using Cauchy's residue theorem that this must be equal to this, pi times the quantity I pi over 2 to the power of k. And so what we're going to do now to try and evaluate this is we're going to let little r go to 0, sort of closing in on the problem point at 0, right? And we're going to let big R go to infinity, so that large semicircle just goes off forever. And the only thing inside of the entire contour that matters at any time is the problem point at positive I, right? And that's how we got this right here, by using the residue theorem. And I'm not going to do it in this video. If Papa Flammy can get away with it, then so can I. I'm just going to sort of state the fact that if you do the proof, it's very tedious, this is going to go on long enough. If you do the proof, these two contours, the ones that go over the two semicircles, they do both go to 0. This one goes to 0 as little r goes to 0, and this one goes to 0 as this one goes to infinity. They really do go to 0. And I'm not going to prove that in this video because I don't want to take the time to do that. If you go through the evaluation of it and do the limit and all that, you'll find that it really is. I just don't want to harp on that. So it turns out that the contour is just equal to the sum of the two horizontal bits, which means there's no problem with us just going to the limits. So we just go from 0 to infinity, and from negative infinity to negative 0, which is of course just 0. Of this function, right? This was the function we wanted to take the integral over. So I'm going to write f of z dz and f of z dz. So right, this is what we wanted to do. So we know that the integral over these two horizontal bits added together gives us this amount here. And remember, this is the thing we're trying to solve for, right? This is the integral from 0 to infinity over this function with respect to z, which is exactly the things we're trying to evaluate, right? To the different powers. That's the integral we're trying to find out. So what we really need to try and figure out is this. Because as soon as we can solve for this in terms of a bunch of k stuff, then we're good. So we need to evaluate this. So right now we are only going to consider the leftmost horizontal integral, which was from negative infinity to 0 over this function. Now what we want to do is we want to try and write this in some way that is no longer an integral, that we can like solve for the integral that we want, which was the one from 0 to infinity that we want to solve for. So the best way to go about that is to try and make the bounds the same as the integral we want to evaluate, which has bounds from 0 to infinity. So the way we're going to do that is make a simple substitution from z to negative z so that these become the negatives of what they are. So what we're going to do is we're just going to let z become negative z, which is a simple statement because it just means that dz becomes negative dz by simple differentiation, and we get that this is equal to, well, what do the bounds become? Negative 0 is 0, negative infinity is positive infinity, and we get the natural logarithm of negative z to the power of k. Actually, I actually wrote n, because just n is still a non-negative integer, just like k was. I'm just using n for now because it'll look neater later on. You'll see what I mean. So n is the same as k, it's just a different letter. So this is the natural logarithm of negative z to the power of n over 1 plus, now what's the quantity negative z squared? That's just z squared again, right? Because a negative number squared is a positive number, so we still get positive z squared in the denominator. And now we just multiply by negative dz, right? Negative dz. But the great thing about that is that this negative allows us to just flip the bounds, right? Taking an integral backwards makes it negative. So we can just eliminate that negative and make the bounds like that. And now look at that. They're the same bounds as the integral that we want to evaluate, the one from 0 to infinity. We just need to do a little bit more manipulation. Now, what we need to do is use the logarithm rule for products and split this up. So this is equal to the integral from 0 to infinity of the natural logarithm of negative 1 plus the natural logarithm of z, all to the power of n, divided by 1 plus z squared dz. And that's just because this is the natural logarithm of negative 1 times z, and the product rule for logarithms is that the logarithm of the product is equal to the sum of the logarithms. It turns products into sums. Now all we need to do is evaluate what the natural logarithm of negative 1 is. And that's not too hard. We know that e to the I pi is equal to negative 1. And if we take the natural logarithm of both sides, we see that the natural logarithm of negative 1 in the principal branch is equal to I times pi. So we can just replace this with I times pi. This actually isn't too bad, because we have the sum of two things to a non-negative integer power, which means we can employ the binomial theorem, right? And when I saw this, I was like, damn, that's actually pretty neat. So we're going to employ the binomial theorem here, which means we're going to rewrite this as a sum over different powers. So those of you familiar with that, this should be pretty clear what I'm doing. Those of you who aren't, look up a binomial theorem. I'm sure you've heard of Pascal's triangle, summing over powers of binomials, things like that. It's quite an interesting little bit of math. So I'm just going to jump right into it, if that's all right. I'm going to rewrite this power of a sum of things using the binomial theorem. So we have the integral from 0 to infinity of the sum from k equals 0 to n of n choose k which is just a sort of function over different factorials. We'll need to represent it that way later on. This is just more compact, so I'm going to use this for now. And it's the first term, which is I times pi, raised to the difference of n and k, so n minus k power. And that's then multiplied by the second term raised to the power of the lower index, so the natural logarithm of z to the power of k. And this is a rewriting of the numerator, so the denominator is still there. 1 plus z squared dz. So we're going to take a look at this now. And I'm going to erase everything above it, and I'm just going to rewrite this, and we're going to take a look at that, okay?